We are living in the age of giant AI, right? These large language models are changing everything. But they've got this one massive, fundamental problem holding them back. They are just colossal. So the big question is, how do we shrink these digital brains without, making them dumber? Let's dive in and figure this out.
I mean, really think about it. When you use one of these powerful AIs, you're not actually running it on your phone or your laptop. Nope. You're pinging a request to some massive, power-hungry data center that could be hundreds, maybe even thousands of miles away. And that right there is the great bottleneck of modern AI. If we really want to unlock its potential, we have to break it out of that cage. And this image, well, it shows you the mission perfectly. The whole goal is to take all that computational power, all that magic that currently lives in these sprawling server farms, and somehow, squeeze it onto the devices we use every single day. Like this laptop right here. It's a journey from the cloud right into your hands. But man, the physics of it, incredibly challenging. All right, so this brings us to our first section, the AI size problem. The sheer physical footprint, the cost, the immense energy these models chew through, it's all becoming a critical barrier. We can't just keep building bigger and bigger data centers forever. We've got to train smarter, not just harder. So what's the solution? Well, the key piece of tech that promises to get us there is called quantization. At its heart, it's basically a compression technique. Think of it like this. You have a stunning, high-resolution photograph with millions of beautiful colors. Quantization is like saving it as a JPEG. It uses a much smaller, more limited palette of colors. Now, the image might be a tiny bit less perfect, but it's drastically smaller and way faster to load. In AI, we're doing the exact same thing, but instead of colors, we're compressing the numbers that make up the model's brain. Okay, next up, the 4-bit frontier and NVIDIA's push for efficiency. So who's leading the charge on this? Well, no surprise here, it's the big players. NVIDIA, the company that literally builds the GPUs powering this whole revolution, is betting big on a new ultra-low precision 4-bit format to completely change how AI is trained. And the numbers they're promising are just staggering. Their latest Blackwell architecture, it boasts a 7 times speed up in these crucial 4-bit operations compared to the last generation. Now, in the world of AI infrastructure, where every single percentage point of efficiency counts, a 7x leap isn't just an improvement. It's a seismic shift. Now, what's really cool is how they actually pull this off. It's not just about, using fewer bits. It's a really sophisticated recipe. First up, they use something called microblock scaling, which gives them way finer-grained control and cuts down on errors. Then they apply what's called Hadamard transforms. This is a clever trick to smooth out any wild outlier data points that could throw the model for a loop. Next is high-precision encoding to make sure the really important values are represented accurately. And finally, stochastic rounding, which is just a brilliant way to avoid systematic bias during the training process. It's like a multi-pronged attack to keep the accuracy high while getting all the benefits of that radical compression. All right, but a polished corporate announcement is one thing. The real world of open source developers, that's a whole other story. So what happens when these shiny new techniques hit the vibrant and, let's be honest, often very skeptical developer community? And this is where it gets messy and super fascinating. This table, which comes from a community benchmark, shows a bunch of different 4-bit methods all tested on the same hardware. So first you've got throughput, measured in tokens per second. That's basically the model's raw speed. And here you can see a method called Marlin is just blazing fast. But then look at perplexity and human eval. These are different ways of measuring the model's quality, or, how smart it is. It's not a simple story at all. Some methods are super fast, but maybe have a little lower quality, while others are slower, but score better on certain tasks. It's a real trade-off. And the community's reaction just captures this whole situation perfectly. One user calls the AWQ speed absolutely cursed, basically saying something has to be plain broken in the test setup to get a number that low. This is the reality of working on the cutting edge. It's often confusing, and results can be really misleading at first. Then another user points out a super important detail. You can't just say GGUF performance is good or bad. Why? Because GGUF isn't a single method. It's more like a container format that can hold all sorts of different types of quantization inside. So the big takeaway here is that out in the wild, performance isn't just one number. It's this complex dance between the hardware, the software, and the specific method you're using. But, speed and size, they aren't the only problems we're facing. As we push these models to learn continuously,
a much deeper, almost more insidious challenge starts to pop up. It's called catastrophic forgetting. Think of it like this. Imagine you train an AI to be a brilliant writer, like Pulitzer-level good. Then you decide to teach it to be a grandmaster at chess. But in the process of learning all those chess moves, it completely, totally forgets how to write. It's like its old skills get catastrophically overwritten by the new ones. And this is a massive hurdle if we want to create truly adaptive, lifelong learning AI.
And this chart right here, it shows you that forgetting happening in real time. Just look at the blue line. That's the standard high-precision model. See how its writing skill, its accuracy on the original language task, just plummets after it's trained on math and then drops again after it's trained on code? It is literally forgetting what it once knew.
So this all seems to point to a pretty simple conclusion, right? Higher precision is better, it's more stable. But what if that's completely wrong? What if the key to better learning is actually less precision? Here comes the surprising twist.
Okay, so just as you'd expect, on the very first task, the full 16-bit precision model, that's FP16, performs the best. I mean, it makes sense, right? It's the most accurate, has the most information to work with. The lower precision 8-bit and 4-bit models, they lag just a little bit behind. So far, no surprises here.
But here is where the twist comes in. After the models get trained on new subjects like math and coding, everything flips on its head. Look at the yellow and green lines. Those are the quantized, lower precision models. They shockingly outperform the supposedly smarter, high-precision model on these brand new tasks. The models we thought were less capable have actually become better learners. So how is that even possible? Well, the leading hypothesis is just fascinating. It seems that the noise, or the tiny imperfections introduced by quantization, actually acts as a form of something called regularization. It basically prevents the high-precision model from getting too rigid and overconfident in the new information it's learning. That little bit of fuzziness makes it more flexible, helping it integrate new knowledge without completely wiping out the old stuff. In a weird way, its imperfection becomes its greatest strength. And this incredible discovery brings everything full circle, right back to our original goal. If lower precision not only makes models smaller and faster, but also makes them better long-term learners, well, that could be the key that finally unlocks powerful adaptive AI on everything from our laptops to the tiniest low-power devices you can imagine. So we're left with this really profound question. We've always just assumed that bigger and more precise is always better. But if shrinking a model can actually make it smarter in the long run, what other fundamental assumptions about AI are we about to see get turned completely on their head? The future of AI in your pocket might be a lot closer and honestly a lot stranger than you think.